Everyone, my name is Alex Lamers. As Randy said, I'm the Warning Coordination Meteorologist at the Weather Prediction Center. My roots are actually there in Central Region. I grew up in the Milwaukee suburbs. I came into the NWS as a SCEP employee at the Milwaukee Sullivan office, and I also worked as a Met intern at the Duluth office. So I'm very happy to be here today to talk to you about WPC Winter Weather Operations and some interesting things we're working on. Always a pleasure to talk to Central Region. And thank you to Randy and Allie for the invite to speak. Next slide. In this presentation, I'll be focusing on probabilistic tools and messaging, the Winter Storm Outlook, or WSO, the Winter Storm Severity Index, or WSSI, and Winter Storm Key Messages. We do have additional information on WPC Winter Weather Services that you can find in our annual WWD Operations course, which should be available on the Commerce Learning Center. I just checked actually the other day and it was there, so it's out there on the CLC now, and the Winter Weather Desk or internal page. I'm not going to be covering everything today, so please do check out those resources. Next slide. So first, a real quick refresher on the Winter Weather Desk. We've increased the number of forecasters in the rotation to 5 for this winter season, and so the desk now supports nearly around-the-clock coverage. This should also provide significant overlap with 2 winter forecasters from around midday into the afternoon to aid with coordination. I would strongly encourage you to reach out to the WWD forecasters via chat or the number you see here with any collaboration thoughts or questions you may have. Earlier in the shift can be better. Next slide. The forecast process that WWD uses is outlined in greater detail in the operations course on the CLC. However, I'll give you a short overview here. Rather than edit the snow and ice forecast directly, many of you are probably familiar with this, our forecasters use a couple control knobs to dial the forecast up or down. These control knobs are generally related to precipitation magnitude, or the QPF, and then the temperature profiles, and we use probability of weather type and snow or ice to liquid ratios. And edits are made to those components, and then the snow and ice forecasts are calculated from there. Next slide. And the responsibility for these edits is shared among 2 forecasters in WPC operations. One QPF forecaster who edits QPF for all areas of the CONUS for days 1 to 3, including non-wintry areas, and one WWD forecaster who iteratively edits the probability of weather type and ratio grids to produce a reasonable snow and ice forecast. We often get asked, who am I supposed to collaborate with? And we would encourage you to not think of the forecasters individually with siloed responsibilities, but rather as a team in constant communication. Therefore, it shouldn't really matter whether you reach out to the QPF or WWD forecaster or WPC more generally. However, I would recommend that for winter weather concerns, even if you expect the edits to be QPF related, to always include the WWD forecasters. They will need to be aware. Next slide. One final note on the WWD forecast process is that collaboration is crucial. Even though we don't publish our deterministic snow and ice forecasts publicly, they are acting as a bit more than just guidance in the whole forecast process. So it's important that we try to align the WFO forecast and WPC forecast as much as possible. And that's because the WPC deterministic forecast becomes the mode of the probabilistic winter precipitation forecast, or PWPF distribution. The variance comes from the overall ensemble, but the skew is based on the position of the WPC forecast, and that affects a lot of downstream products, including the snow and ice probabilities, but also the winter storm outlook and a new probabilistic version of WSSI. More on that later. Therefore, coming to consensus is important. Next slide. And I'm just going to shift gears a little bit now. What you see here is basically the result of a simple image search for snow forecasts. This isn't all precisely the same event, but I think it provides a fairly good spectrum of how snow forecasts reach the public right now. And I do think a few things jump out immediately. Different colors, different ranges, different forecasts, everything is different. And if there's one thing we know about communication, it's that consistent messages break through. We're not really singing from the same sheet of music when it comes to winter storms. And for some reason, a lot of people really want to produce their own snow forecast. It's just the way it's always been, and across the weather industry. And that's way different than what you see happen in other weather hazard events like a hurricane, for example. And So we're headed into snow map season now, and you'll probably see more of these examples over the next few months. The other thing that jumps out here is just how often the forecast is communicated in deterministic terms. And I do think we can do better than this. And I don't think I could have picked a better lead into this presentation than the one we just heard. And I do think probabilities are the way forward. And so this should dovetail nicely with everything we just heard. Next slide. This is a simple but eye-opening bit of verification that was run by Bruce Feenheis in our development and training branch. And this is 5.5 months of data from last winter for areas east of the Rockies. And the GFS is depicted on the left and the European is depicted on the right. And if you look at the X or horizontal axis, you can see forecast amounts from that particular weather model. When you go vertically and use the different colored lines, you can see how often analyzed snowfall occurred relative to that particular model forecast snowfall. For example, if you look at when the GFS forecasted 10 inches of snow, the observed values were between 1 and 11 inches 80% of the time. It was basically less than half the forecast amount, or less than 5 inches 50% of the time. So that's an enormous variation from a deterministic forecast, and that's to be expected. That's the danger of model snow maps that float around with every snowstorm and just any deterministic forecast in general. Even if you get the structure of a winter storm correct with a deterministic forecast, small errors in the placement of heavy bands and the track of the storm can create huge deviations from the deterministic forecast. So keep in mind that these stats are also for day one forecasts as well. This is not like a 3 or 4 day out type thing. And I think this powerfully illustrates the case for probabilistic forecasts. Every deterministic forecast is going to be wrong. It's just a matter of degrees of wrong. Next slide. And real quickly, I'm just going to go through some of our probabilistic verification. In general, you can see snow probabilities are fairly reliable. This is for last winter, and WPC is on the left and NBM is on the right. A perfectly reliable forecast would fall along the magenta line. In other words, when we say something will happen 20% of the time, it actually happens 20% of the time. NBM shows good reliability overall and is slightly overconfident at higher forecast probabilities. And WPC is fairly reliable at low and very high probabilities with some overconfidence in the intermediate probability ranges. Overall, though, these are pretty solid results and suggest these forecasts will provide useful information over many cases. Next slide. We also have reliability verification for freezing rain probabilities based on the ASOS ice sensors. This is for WPC PWPF only. And I have the 0.01 inch and 0.1 inch thresholds available here. As you get to higher thresholds and higher forecast probabilities, the sample size gets small and it may affect the results. You can see some of that noise here. However, for the more reliable data at or below 60% forecast probabilities on both of these charts, you can see the probabilities are quite reliable. Next slide. I also wanted to show you some data for more than one winter season so you can clearly see the trend in improving reliability with our PWPF with time. In each bin on both charts, you'll see there a WPC deterministic snowfall value along the x-axis. And we then evaluate how often observed snow fell into the 3 buckets you see depicted here, over the 90th percentile in green, between the 10th and 90th percentiles in orange, and below the 10th percentile in blue. As you can see, 2 winters ago, we tended to see snow lower than the 10th percentile a lot more often than 10% of the time. However, that bias was considerably reduced last winter due to some tweaks that we made. Next slide. Finally, all the verification data you've seen has been mostly from our short-term forecast, but I did want to show the verification from our medium-range winter probabilities. The WWO is technically the probability of 0.25 inch liquid equivalent snow and sleet, but we ran verification against 2.5 inch accumulations on no risk for simplicity. And overall, you can see these probabilities are quite reliable as well. One thing to note is the WWO is not necessarily the same ensemble each shift. The medium range forecaster can choose which ensemble systems to blend, so the membership is not static from run to run. Next slide. Before we get into the rest of the presentation, I did want to pause with a few takeaways on probabilistic winter forecasts. Overall, the probabilities are fairly reliable. That's one takeaway, and that should make them quite useful for both understanding the forecast and communicating it to partners in the public. I know that we all get asked for the deterministic forecast a lot, and that will still be the instinct for a lot of people for a while. Just tell me how much snow I'm going to get. However, when you think back to the slide with all the snow maps on it, I think we can do a better job of making sure probabilistic information doesn't get lost in the shuffle. And I'm so excited about the messaging experiments that you've been doing with probabilities there in Central Region. And I think the probabilities offer an anchor for consistency and to be honest about the state of the science. Different offices and forecasters will always have some level of disagreement, but probabilistic information can give us a more stable platform to build a message on. And of course, communicating with probabilistic information is still relatively new, and I can't pretend like we have all the answers here at WPC, so I'd love to stay in touch and learn from each other. Please reach out to me if you have any success stories to share or any feedback. Next slide. Of course, the probabilistic information can be very useful when you're creating the forecast, not just communicating it, and the probabilities can allow you to evaluate how extreme the forecast is relative to the distribution, where the uncertainty is greatest, and all that. WPC is a resource in this respect, so don't hesitate to chat or call if you have questions or thoughts. In addition to all the probabilistic data, we also have some cluster analysis tools that we continue to develop. I can't get into those in detail today due to time, but it follows along this general line of thinking. So please reach out. Next slide. We do have some tools you can use to dig into the ensembles yourself, and they're all available from the WWD internal page. And I have the link to the page shown here. Many of you are probably familiar with this, but if you scroll down on the panel on the right side of the page to the forecast, outlooks, and impacts section, you'll find the links I'm about to show you. Next slide. The first one is the WPC Super Ensemble Viewer, which allows you to look at plan view maps of all the individual ensemble members that are driving PWPF for days 1 through 4. This is available for QPF, snow, and ice. And you can look at take a look at the ensemble mean, WPC, NDFD, and the NBM as well. It takes a little while to run all these images, so depending on when you're working on the forecast, you may only be able to see the previous cycle's ensemble data. Next slide. Next, we have the WPC Super Ensemble Plumes, which allows you to more clearly break down the range of ensemble members at many individual points across the country. Every CWA should have several of them kind of sprinkled across your area. You can turn individual members on or off, evaluate certain model cores, and look at a dprog DT for the ensemble mean. Most of the model cores are shaded in similar colors. The European is in blue, the GFS is in green, Canadian is in orange, and high res is in purple. And in the screenshot above, you can see a lot of orange lines below the thick ensemble mean line, and that indicates Canadian members are generally less snowy. And that's kind of, I think, really useful information that you can dig out of these. Next slide. Finally, we have some internal medium range probabilities available. These are not to be shared externally. They're internal for now. These probabilities account for all the members of the GFS, European, and Canadian ensembles and do not necessarily follow the same methodology as the WWO, which I mentioned earlier. Nevertheless, this is a good resource for situational awareness. I know it can be frustrating to have different sets of probabilities and products available at different time ranges. I've heard that feedback personally from a variety of folks. Please know that we hear and understand that we're working to build a consistent winter product suite from days 1 to 7 in the near future. So hopefully this is stuff that you can continue to leverage more and more and more over the coming years. Next slide. One application of WPC probabilistic information is the Winter Storm Outlook, which basically takes a slice through the probabilistic data at the watch warning threshold at individual grid points across the CONUS. And this then creates a probabilistic map like you see on the right side here. Given that it uses the watch warning threshold, it is both potentially useful for watch collaboration and as an early alert generally to external users to potentially significant winter storm threats out to day 4. Of course, it's merely for snow and ice accumulation, so complicating factors such as wind and mixed precip would not be reflected. Next slide. We had a summer student run some verification data on the WSO, and specifically what the WSO values were in individual forecast zones when a watch decision was made. So what the WSO showed when you issued the watch, more or less. And as you can see, the average WSO value in a forecast zone when a watch was issued was just over 0.2, and the sample size was over 6,000 zone events. The most common scenario was actually for a watch to be issued with a WSO value of less than 10%. That was true across the CONUS, but the trend was especially common in Central Region, the first grouping on the chart on the right side of the slide. Almost half of Central Region watches were issued with a negligible WSO probability, and I'm going to get into some possible explanations in a moment. Next slide. So we also evaluated how many of the zone events in each WSO bin verified, and verification was based on the event types you see here in official NWS storm data. Generally speaking, watches issued with a higher WSO value verified at a higher rate. Verified is in blue and unverified is in red, which is what you would expect, and that's an encouraging result. Also, about half of the watches verified overall, which is also close to what is prescribed in directives at a 50% confidence threshold. So that's also encouraging news. The distribution you see in the chart here is similar for all NWS regions. You can also see the average WSO value is highest for watches issued for events driven primarily by accumulations, and that's what we would expect. So ice storms, heavy snow, and winter storms. The WSO values were lower on average for blizzards with a combination of wind and snow, and for lake effect events, which can be difficult to resolve in some of the global models that comprise our winter ensemble. Next slide. We created a variety of maps showing variations in the data from WFO to WFO, but I will show you just two today. Here's the average WSO value at watch decision times, and you can see that there are fairly low averages in Central Region. This was a little surprising. Remember, the WSO is simply a combination of PWPF and local criteria thresholds, and we know PWPF is fairly reliable. If anything, it's overconfident. And we had a few possible hypotheses that included, number one, forecasters may be shifting to more impact-based decision frameworks, even though the criteria written on paper may be higher in some cases. Number two, wind and mixed precip types were lowering decision thresholds in some cases. And three, the difference between point and zone probabilities. So the WSO is calculated at individual grid points. However, a watch is issued for an entire forecast zone. That's a bigger target to hit. And so the probability of a zone being impacted is always going to be higher than the probability of a specific location in that same zone being impacted. So I think it's probably a combination of all three, but we're going to focus on the first one in this presentation. Next slide. The other map I have here is the proportion of watches issued with a value of less than 10% on the WSO. The vivid red colors indicate a majority of the watches were issued with the WSO showing less than 10% probability. And you can see that was the most common last winter in the northern and central plains. Next slide. And I didn't find the bulk verification to offer a satisfying explanation, so I created these scatter plots of all the WFO's data to evaluate things. And after skimming off the WFOs with the lowest 20% sample size, I plotted the remainder here, the average WSO value for each WFO along the x-axis, and the percentage of watch zone events that actually verified along the y or vertical axis. So if you move up, as you move up the chart, those WFOs verified more of their watch zones, and as you move right, they typically issued watches at a higher WSO value. The size of the bubble varies with the sample size, and averages are plotted in thick black lines. And the pattern seems pretty random at first glance, but there's important patterns buried within. Next slide. One thing that's fairly evident, most of the offices with a lot of at-bats or a larger sample size fall within one standard deviation of the mean. So this is somewhat encouraging and suggests perhaps there may be less randomness when we have more than one winter of data and as offices encounter more and more events. Next slide. I also noticed that many of the remaining larger sample size offices fit the pattern you generally expect, that WSO should have some correlation to the verification rate given that the underlying PWPF is reliable. And this was also encouraging. In the lower left, offices that issued watches at low WSO values tended to have less of their watches verified. And in the upper right, offices that issued watches at a high WSO value saw a lot of their watches verified. Another thing that jumps off the page when you zoom out is that a lot of the dots are skewed toward the top left part of the diagram. In other words, there's a lot of offices that issued watches at low WSO values, but verified considerably more than half of their watch zone events. And that's the part of the diagram that didn't really make a lot of sense to us. So next slide, and we can dig into maybe the reason why. I kept coming back to two components of the WSO, the underlying PWPF and the threshold set by local criteria. And the thresholds are a critical element of the WSO. They really drive the probabilities. So any difference between what's written on paper and how forecasters are calibrated would tend to show up in the verification data set. So I decided to do a simple comparison of the WSSI moderate snow amount thresholds, something we generally message is roughly equal to a warning level impact, and the legacy criteria used in the WSO. It's of course not perfect, but WSSI snow amount thresholds are based on a detailed snow climatology across the country. So big differences between that and the watch warning thresholds may be instructive. And I do want to emphasize that forecasters being calibrated to impacts is a good thing, in my opinion. It's a valuable service to partners and communities. However, it does limit the WSO specifically if impacts tend to occur at lower thresholds than legacy criteria would indicate. So that's the narrow issue that we were evaluating with our verification. Next slide. The map on this page visually shows where the difference between 24-hour watch warning criteria and the WSSI moderate snow amount thresholds were largest. And the beige or yellow shading is close to 0, and the orange and red shadings indicate larger differences, with the legacy criteria being set several inches higher. You can see I have the 3-letter WFO IDs plotted in red text on a variety of offices where the threshold differences are larger. And I'm about to show you the scatter plot again with these specific WFOs highlighted. Again, it's not necessarily a critique of the watch strategy at these offices, and I think being calibrated to impacts is a good thing, but we're just trying to identify whether something systematic is happening here. And this suggests they do have something in common. The legacy watch warning criteria is set at a level that's more rare in their local climatology than some other offices in other parts of the country. Next slide. So here's the scatter plot we've been looking at, and I've drawn a red triangle on here to roughly indicate a space where watches verify more frequently than you'd expect based on the corresponding WSO values. You can see all of those offices in the larger threshold difference areas on the previous slide. I plotted in red here. And to me, this seems like a decent indication that forecasters have become more calibrated to what causes impacts instead of a simple and binary yes/no criteria. And the gap that's emerged poses some challenges for the WSO because we're currently leveraging that simple criteria. We've had some discussions about how to build greater complexity into the WSO, perhaps leveraging the probabilistic WSSI. However, I do want to reassure you, given the data you've just seen about the WSO in Central Region, that we're looking at more data to help support watch decisions and collaboration calls than just the WSO. So there's a lot of tools in the toolbox, and this is just one of them. But I do think it points to a need to reimagine the way we think about criteria for winter storm watches and warnings. Next slide. And we're going to close with one of the other tools in the toolbox, WSSI. Many of you are probably at least somewhat familiar with it, but if you haven't spent much time evaluating it, I'd encourage you to use the WSSI webpage this winter during live events and provide us with any feedback you may have. One thing we emphasize often is WSSI is merely attempting to forecast a general level of potential impact from a winter storm, not forecast specific impacts such as schools closing at a moderate impact level. So it's designed to capture an overall potential impact to society, which can, of course, be mitigated through protective measures from individuals, organizations, and governments. So I think it's key we frame it as a potential impact level. We've had feedback on the impact category descriptions on the high end of the scale. And there's ongoing funded social science work evaluating the colors and descriptions. So hopefully we have more news on that in the near future. In the meantime, if you don't think the impact descriptions necessarily apply in a certain case, I would recommend just using the category names if you were to share this instead. And we extended experimentally to day 4 this year using some extra data from WPC and the NBM. Days 1 to 3 are still driven by the NDFD forecasts. And there's a new rolling 24-hour display. And we have an information drop-down menu with a lot of resources that you can use in outreach or to point people to. Next slide. I'm not going to belabor this point because I think a lot of you are relatively familiar with WSSI, but the overall WSSI level is composed of 6 different winter weather hazards shown on this slide. The maximum WSSI value comes from the highest value of the individual components. So you got snow amount, snow load, ice accumulation, blowing snow, ground blizzard, and flash freeze. Next slide. WSSI also does account for some non-meteorological factors in the impact level calculations. So urban areas are used for the ice accumulation and snow amount components to give a 25% boost to the raw impact values. This does not automatically bump WSSI up the next impact category. So for instance, a raw value of 1,000 would be increased to 1,250, for example, over Chicago. And then those raw values are fit into calibrated appropriate categories with these numerical ranges before displaying the actual category on the public webpage. Land use is incorporated into the blowing snow and ground blizzard components to decrease impacts for areas with reduced wind through friction, such as dense forests and areas with high density of buildings. And forest type is used in the snow load component because conifer trees can handle more snow than deciduous trees. So overall, the meteorology is going to drive your impact levels, but these are important nudgers that are accounted for. we have received comments and feedback on other non-meteorological elements, such as rush hours or days of the week, and those are being evaluated but are not currently incorporated into WSSI. Next slide. I'll show you two quick examples. The first one here is a snowstorm in West Texas. So the standard forecast here called for a swath of 7 to 9 inches of snow, shown in yellow shading on the left side, which was then converted into a swath of major impact in WSSI over parts of West Texas from near Midland up to near Wichita Falls. And this makes sense if you think about it logically. That much snow in Texas would be a huge deal. Midland only averages 4 inches of snow a year. So WSSI leverages a dense network of snowfall data over the past several decades to help answer the question, how unusual is this amount of snow in this part of the country? So it's basically aware of facts like Midland only averaging 4 inches of snow a year. And this can even account for differences in snowfall patterns within individual counties. So it is more precise than the winter storm outlook. Next slide. The second example here is from Central Region. It's a ground blizzard in the northern plains. And you can see the gradient and impact levels over Minnesota, where the WSSI more quickly drops off due to increasing forest cover. Remember, the blowing snow and ground blizzard components consider land cover in their calculations. So this makes WSSI more sophisticated than a simple calculation using just snow and wind. Over the open plains of northeast South Dakota, the higher impact levels generally verified, as the two webcam images from the height of the blizzard show from the Aberdeen office. Next slide. And big news, Probabilistic WSSI, the updated page is now live. Last winter, we internally tested a version of Probabilistic WSSI for the snow amount component only. This winter, we have some major upgrades that we're excited about. This expanded to include all the WSSI components except ground blizzard and flash freeze, and it's extended in time out to day 7. So the new page was just launched and it's available from the WWD internal page. I'd encourage you all to check that out and let us know if you have any thoughts. The probabilistic input data is from the WPC Winter Storm Ensemble. And remember, this is only for internal use for now. Next slide. And before we wrap up, I wanted to briefly mention our winter storm key messages. We have been doing these for a few years in an experimental fashion, mostly sharing them through social media graphics. The intent is similar to NHC's key messages for hurricanes. They should highlight the agency's most essential information for upcoming major winter storms. So it provides a brief summary that can be useful to users on the state, regional, and national level who may not have time to evaluate information from numerous WFOs across the country. We have some guidelines on what constitutes a large-scale storm listed here, but we do allow for some forecaster discretion. The idea is that we want to capture events that stretch across many WFOs and let WFOs handle things on the more local level for things that are contained to smaller scale. For this winter, we also plan to initiate key messages for larger regional scale ground blizzards and snow squall events that stretch about a couple hundred miles in at least one direction. We hope this elevates awareness of those events. The idea is that we should be in sync with and complement local messaging with this, not be in conflict. So we do have collaboration protocols. On the day shift, we tend to work this through the rocks, but if they're unavailable, WPC will coordinate directly with WFOs. And this year, we will be including the key messages in the heavy snow discussion text product as well. Next slide. And here's a few takeaways. I do want to underline that we welcome thoughts and collaboration. Please reach out with any ideas, questions, and best practices you may have. We're glad to participate in blue sky engagements with your offices, so it doesn't have to be collaboration during an actual event. And that can extend from workshops and seminars to post-event reviews to exercises. If we have any time left, I can take some questions. Otherwise, please reach out via email to any of the points of contact you see here, including myself.